Adam Ward here, talking today about dimensional analysis. In preparation for this video, you should have watched me talk about some background and motivation, why we generate dimensionless numbers, and I introduced this idea of Buckingham's pi theorem. That would be sort of the method that we use to get to these dimensionless numbers. And rather than talk about that in an abstract way, I thought that what I would do today is just work through a problem and help you see how the steps of this go. Okay, so here's Buckingham's pi theorem in 8 user-friendly steps. Let's get to it. So the problem for us today relates to airplanes, and we want to derive some dimensionless numbers that help us predict how much drag there would be on an airplane. So drag force is represented by that F sub d, that red arrow behind the airplane. So this is basically shear forces pulling on the airplane to slow it down as it's trying to move through the fluid, or as the fluid air passes around the airplane. And what we're told is that we know that this has something to do with fluid velocity v, with the fluid properties themselves. So you can see density and viscosity, and with the size of the airplane represented as an L. And throughout this problem, just for clarity, I'm going to switch that to like a script L, just so that the length of the airplane is clearly script L, and capital L will be the length scales as a dimension. So our goal here is to take this relationship and describe it with dimensionless numbers. So, Buckingham pi theorem time. Step 1, list all the variables involved in the problem. Now, when you're doing this out of a textbook problem, it's extremely easy to do this. They're given. If you are doing this for your own research project, you really want to reflect and ask yourself, have I thought of all the variables that might matter? A good way to do that is to review the literature or review any empirical data you can get your hands on, and try and make sure that you have all of those variables listed. So list all the variables, check. Step 2, list the dimensions for each variable, and you need to either pick force length time or mass length time units, FLT or MLT. And so the variables that we're going to consider here include fluid properties, they include the geometry of the problem, they also include any external effects. So what's going on outside the airplane that might matter. All right. So in this problem, I've elected to use the MLT or mass length time version. So a force, I'm representing it here with a mass multiplied by a length per time squared. And again, I always remember conversions between F and M by remembering F equals ma, force equals mass times acceleration, and I always have to write that down to get my units correct. Length is easy, that's just a length scale. Velocity is a length per time. Our viscosity can be represented as a mass multiplied by a length per time. And density is a mass per unit volume. And of course, a volume is a cubic length. So step 2 in Buckingham's pi theorem, not too bad. List out all of the dimensions for each of those variables. Now, I just want to note here, and you can see me writing in red, if you decided to work this problem in FLT units instead of MLT units, you would diverge from my workflow here. It is absolutely acceptable to do that, but if you do, then your fluid properties are going to need to be expressed not with masses in those terms, but with forces in those terms. And so that is absolutely an option, and Buckingham's pi theorem will end up at the same result. In this problem, I picked MLT. I have no basis for picking one or the other. That was just a somewhat arbitrary decision I made. Okay. Step 3, how many pi terms are you going to need? How many dimensionless groupings of variables are we going to generate? And so this is a simple calculation. The number of terms you need is equal to the number of variables you have minus the number of dimensions you have. So in this problem, we have 5 variables. Those are written in black across the top of the page. And we have 3 dimensions. We have mass, length, and time. It is possible that you don't have 3 dimensions. Perhaps you have a problem in which time scale doesn't show up or length scale doesn't show up. But in this case, we have 3 dimensions. So 5 minus 3 equals 2. We're going to look for 2 pi terms. And so at the end of the day, the relationship we're after is going to look something like this. Pi 1 is equal to some function, so that phi that's written here, it just means some function. We don't know what that relationship is, but we know there is a relationship. So pi 1 has some relationship to pi 2. Now, the reason you care is because that is substantially simpler than what we started with. We started with force has some relationship, some function of 4 variables. Now we're describing a normalized version of force, pi 1, as related to one other thing. So we've basically gone from 5 things to keep track of to 2. So that's the benefit of Buckingham's pi theorem and doing this non-dimensionalization. It simplifies the parameter space. All right. So we've listed our variables, we've got their units, we know how many pi terms we need. Onward. Step 4 says select the repeating variables. It would be helpful for you all to know what a repeating variable is. So each pi term has what I call an anchor variable. So that's the thing that you're starting with. And what you're doing is combining that anchor variable with repeating variables to cancel out all of the dimensions. Okay? And I'm fairly certain that this idea of an anchoring variable is just my own way of thinking about the problem. This is probably not something that's written in whatever textbook you're looking at right now, but it's how I think about it. So let's take a look at the variables that we've got here. We need to decide how many are going to be anchors and how many are going to be repeating variables. So how we do this? Step 1, the thing you started with, the left-hand side, the property that you're trying to predict is definitely going to be an anchoring variable every time. Now, because we know we need 2 pi terms, we know we need 2 anchoring variables. So 5 variables total, 2 serving as anchors means 3 of them will be selected as repeating variables. Picking repeating variables, perhaps more of an art than a science. I'll tell you what I think about. So how do you pick those repeating variables? First off, the group of repeating variables you pick has to include all of the different dimensions. So this is an MLT problem. Whatever we pick for our repeating variables have to include at least one of them somewhere has to include a mass, a length, and a time. Not each variable, but taken together, M, L, and T have to show up. Number 2, I try to pick repeating variables that are simpler. So, for example, something with units of length is easier in the long run to work with than something with units of length squared, time over mass cubed. I just made that one up. And finally, I try to pick variables that look different. So for example, if you have 2 variables, one with units length per time and one with units time per length, those don't look very different, and that's going to ultimately confuse the matter and cause you some heartache. So I try to pick variables with units that look different. So in this problem, I'm going to select length, velocity, and density to be my repeating variables. Those satisfy the required criteria of including mass, length, and time. And those satisfy my personal criteria of my repeating variables having the simpler units, where my anchor variable has more complicated units. So that's how I made the decision. Step 5, make a pi term. All right, so your first pi term is always going to be, this is the left-hand side of the equation. This is the pi term that's got that first anchoring variable associated with it. And we're going to set up an equation here. that has our anchoring variable multiplied by the first repeating variable raised to the a power, the second to the b power, and the third to the c power. In our example here, it looks like this. Pi 1 is going to be equal to that drag force multiplied by length raised to some power, velocity to some power, and density to some power. So if we can find a, b, and c, we've got a pi term. How do we find a, b, and c? Right now we've got one equation and three unknowns. That doesn't bode well for us. Excuse me. So what we're going to do is we're going to take each of those terms that I've written and we're going to assign it the units that we want, that we know go along with it. And I'm going to use color on this slide to just help you guys see where these terms are all coming from. So our pi term is unitless. So on the left-hand side in black, you can see I've got m to the 0, l to the 0, t to the 0. And that has to be equal to our drag force, which has units of mass length per time squared. And so I'm showing you there, although we normally write it with time in the denominator, I'm going to strongly encourage you to write what would be in the denominator to use that negative sign notation. And at least initially, putting m to the 1 and l to the 1, even though something raised to the first power is that thing itself, those ones will turn out to be helpful to you as a strategy. And so we can go ahead and do that with our length of airplane. Script L has units of length, L. Velocity has units of length per time, raised to the b. And our density has units of mass per length cubed, raised to the c. So you can write three equations here based on each of those terms. So we know that at the end of the day, when you multiply together all of those coefficients, all of the m's need to cancel out, right? And because when we multiply exponents, what we're functionally doing is adding them together, we can write an equation. So for mass, we see that 0 on the left-hand side, 0, has got to equal 1 on the right-hand side, plus 1 times c. And that 1 times c comes from the density term. Right? There's no mass in green, there's no mass in red, so those don't show up. But we do have a 1 times c. So this is giving us 1 times c. So that's where this comes from. You can do the same thing for length, where, let me grab a different color here, I'll use a pink. 0 on the left-hand side, we've got a 1 in the purple term. We've got length raised to the a power in this green term here. So we have 1 times a, and you can see that I was lazy and just wrote plus a down there. Similarly, in that next term, we've got 1b, and again, I just wrote a b down in that equation. And in this third term, we've got a minus 3 multiplied by c. And so those show up as minus 3c. So what we're doing is we're taking those dimensions and we're turning them into these separate descriptions of the exponents for masses, the exponents for length, and finally the exponents for time. And you can see time has contributions from that anchor variable in purple and from velocity, where time is in the denominator. So what you've done now is you've got a solvable problem. You've got 3 equations and 3 unknowns. And so you all can do the algebra of this problem, and what you find is values for a, b, and c of -2, -2, and -1 respectively. What does that mean? That means your pi term looks like your anchor, FD, multiplied by that script L raised to the a power, or -2, velocity raised to the b power, -2, and density raised to the c power, -1. You can also write that a little more cleanly by taking those negative signs and remembering those mean in the denominator. So you could express it as pi1 is equal to that drag force divided by length squared, velocity squared times density. That's it. That's our pi term. So that's our first pi term. Step 6, repeat step 5 for any other anchor variables that you have. And so in this problem, we had a total of 2 anchor variables, 2 pi terms that we were after. So we've got just one time to repeat this. If you have 6 anchoring variables, you're going to have to repeat that step 5 more times. So a total of 6. So let's see if we can do this with a little bit less explicit use of color here, because the setup is exactly the same. Right? You can see that I've swapped in a new anchoring variable, but all of those repeating variables stay the same. Hence, they are repeated. So using the exact same strategy here, we know that on the left-hand side, we want no units. Mass to the 0, length to the 0, time to the 0. On the right-hand side, we need to have the units that go with our new anchoring variable, mass, length per time, and then the exact same strategy we used before for length, velocity, and density. We've got those units written down raised to the a, b, and c power. If you had 5 repeating variables, then they would be raised to the a, b, c, d, and e power. If you had only 2 repeating variables, you would just have an a and a b there. But always, what will turn out is that you can write these equations for the mass, the length, and the time dimensions. Right? And so, again, just to drive it home, these numbers out front that I'm dashing with purple right now, those are associated with the anchor variable, and all of this stuff with the terms that contain letters, those are all originating from the repeating variables. So once again, you can solve that system of equations and find a, b, and c all turn out to be -1 in this case. So here's your second pi term. It's your anchoring variable, mu, multiplied by the inverse of length, velocity, and density. Or cleaned up a little bit, we could write it this way. Now, that's our second pi term. That's great. Just one quick note for those of you keeping score at home. That's actually 1 divided by the Reynolds number. And so the reason that Reynolds number is a thing, it's not because Reynolds was particularly famous more than anyone else. It's because this ratio shows up in so many fluid mechanics problems. And the reasoning that it shows up, you might recall, is that it's got the fluid properties, it's got the geometric scaling, and it's got the kinematic scaling all wrapped into one. So Reynolds number is one of these really common variables. It shows up so much that we've given it a name. We've defined it as Reynolds number, just to shorten our workload. Okay, so we've repeated step 5 for our other anchoring variable. We've got a second pi term. Step 7, check your work. So at this point, if you have done Buckingham's pi theorem correctly, these should be dimensionless. What I'll encourage you to do is always check that. So you can see here I've written the units for drag force in purple, for 1 over my length squared in green, 1 over velocity squared in red, and 1 over density in blue. At this point, we can then go through and say, yep, mass over mass. We can cancel those out. I've got a total of 4 length scales in the numerator, 1 in purple, 3 in blue, and I've got 4 in the denominator, 2 green, 2 red. Those all cancel. I've got a time squared and a time squared, and I feel good about myself. My first pi term did work. Pi 2, I'm going to be lazy in this example problem. Since we know it was 1 over the Reynolds number, 1 over something unitless is unitless itself. So we should always go through the trouble of checking these units and making sure that these are actually unitless numbers. If you're doing a homework problem, a quiz problem, you're doing this in your future career, this step of checking your own work is the number one way that you can find if you've made a mistake through this Buckingham's pi theorem. So we've checked our work, we feel good about our pi terms, and so we can then write the final form of the relationship, which should look like pi 1 is some function of pi 2, or in this case, plugging in the actual pi terms. So this terminology written here, that is the ultimate answer that we were after. You'll recall we were asked to derive a relationship that had dimensionless variables that describe the problem, and this is where we ended. So after all of Buckingham's pi theorem, we had drag force is some function of length, velocity, density, and viscosity. And what we've done is we've transformed that from being a 5-variable relationship to a more simple 2-variable relationship. We still don't know the functional form, right? We used to use a script f, now we're using a phi. This is still unknown, but the problem is a heck of a lot simpler because now we just need to relate these groupings to one another, not cycle through every combination of every possible variable that was going into this problem. All right, folks, I hope this is a helpful explanation for you all. I'm going to sign off on this one, and I will get a few more examples pulled together in the coming bit, or if you're watching this on the web, then they exist instantly, probably down here. All right, see you, everybody.